Hola, espectadores. Good morning. Gonna wait for a couple more viewers before I start. Once again, I cannot stop yawning. Supposedly the temperature is going down in the next couple days. Only 84 today. Then down into the 60s Saturday and Sunday. Wowie. Okay. Yo comienzo mi lección. Yo empiezo mi lección. It is going to be good running weather. I'm psyched. Okay. So we are moving on from forces to our next topic. Our next topic is called energy. It's a great topic. Okay. So energy is a quantity that a physical system has, and it basically it's a quantity that decides what can happen and what can't happen. If you have enough energy to do something, then there's the possibility that you can do it. If you don't have enough energy, then it's impossible to do it. Okay. Energy is measured. So energy is denoted by E. And energy is measured in units called joules. Okay. This is abbreviated by J. So you have a certain number of joules of energy. Another unit of energy that we won't use in this class, but is also common, is called the calorie, capital C calorie. And 1 calorie is 4,186 joules. Okay. So when it's said that the daily recommended caloric intake is 2,000 calories per day, what they're saying is you should consume a certain amount of energy. You should have a certain energy input. Okay. If the amount of energy that's coming into your body is greater than the amount of energy that you're using, then you're going to put on fat, basically. So what we're going to do, there's a number of different types of energy. Okay. And we're going to talk about three different types of energy today, and then in the next lesson we'll talk about some other types of energy. So the first type of energy that we're going to discuss today is called kinetic energy, which is denoted by K. And kinetic energy is the energy of motion. So this is the most common form of energy. It's kinetic energy. In order to have kinetic energy, you have to be moving. So what is the formula for kinetic energy? The formula for kinetic energy is 1/2 times the object's mass times the object's speed squared. So this is kinetic energy. So we can see why it's the energy of motion, because the faster you go, the more kinetic energy you're going to have. Okay? So this is a really common form of energy. Another common form of energy is what's called a potential energy. Okay? And anytime you see this term potential means energy due to position or due to configuration. Okay? That's what a potential energy is. It's an energy due to the configuration of something. So, and there's lots of different types of potential energy. For example, there is chemical potential energy, which is the energy due to the configuration of molecules. So gasoline, for example, has chemical potential energy. The configuration of those gasoline molecules gives it energy. Food has chemical potential energy. There are also things like electrical potential energy. So if we think about a storm cloud that's about to have a lightning strike, it has chemical potential energy. Okay, but the form of energy that we're going to focus on today is called gravitational potential energy. And that's energy due to position in a gravitational field. All forms of potential energy are going to be denoted by U. Okay. So to distinguish the different forms of potential energy, I'll just put a little subscript right here. And so for gravitational potential energy in particular, it's U sub G. And the formula for gravitational potential energy is M times G times Y. So you know what M and G are? Mass and acceleration due to gravity. Y is the elevation. Okay? So if you have an object and you raise its elevation, you are giving it gravitational potential energy. Okay? If you lower it, you're taking away gravitational potential energy. If you move it from side to side, you're not changing the elevation, so the gravitational potential energy stays the same. Okay? So one of the things about gravitational potential energy is that you choose where y equals 0. You have the freedom to choose where y equals 0. All right. So what if I have three objects, A, B, and C, like this, okay? And what if I called y equals 0 right here? Good, man. Gonna slap myself. I got plenty of sleep last night. I don't know what the deal is. I think it might be because the mornings are getting darker and darker, you know. So it's yeah. Okay, so if we look at object A is above the line y equals 0. Okay, so that's going to have positive gravitational potential energy. Object B is at y equals 0, so it's going to have 0 gravitational potential energy because it would be m times g times 0. And then object C is below the line y equals 0, so it actually has negative gravitational potential energy. So it is okay to have negative gravitational potential energy. All right. However, what if I decided to redefine where y equals 0? Like maybe I redefine y equals 0 to be right here. And in that case, all three of them are above the line, so they all have positive gravitational potential energy. Okay. It turns out that with energy, what matters is gravitational potential energy differences. So basically the ranking, which one has the greatest, is going to be A, no matter where you choose y equals 0. So you get to choose where y equals 0 is. Just choose it to be a convenient spot. It's up to you. Okay? Another important form of energy is called heat, also known as thermal energy, also known as internal energy. Yeah, so the elevation is relative. There's a question about elevation, and the elevation is relative to wherever you define y equals 0 to be. So if you're using this line to be y equals 0, then the y value for A would be this distance. If you're using this to be y equals 0, then the elevation would be that distance. Okay? So heat, or thermal energy, or internal energy, is the energy of random atomic motion. Okay? If we zoom in on any object, all objects are made out of atoms. Okay? So we zoom in, we have an ultra powerful microscope. We zoom in and we look really close at the tip of my finger, for example. So close that you could see the individual atoms. Those individual atoms are not going to be at rest. Atoms are never at rest completely. They are always jiggling. Okay? So they're going like this. They're jiggling. The atoms are jiggling all over the place. And so really that's a kinetic energy. It's a microscopic kinetic energy of all these atoms jiggling around. Okay? So that if something is really hot, if it has a high temperature, then that means that those atoms are jiggling extremely quickly. Okay? So that's called thermal energy. It's a form of energy that is the energy of just random atomic motions. Okay? So these are the three types of energy that I wanted to talk about today. There is something called the total mechanical energy. Oh my gosh, come on. Which is denoted by capital E. And it's equal to the kinetic energy an object has plus the potential energy it has. Okay? So you add the two up and you get the total mechanical energy. Let's do a little example. I can't stop. I'm just going to draw a picture. Okay, so let's suppose we have a bird. Okay, I guess that's a bird. I don't know, it kind of looks like a maple leaf / bird. And let's say that the bird is going this way at 11 meters per second. It's going to the left at 11 meters per second. The bird has an elevation of 12 meters. And the bird has a mass of 1 kilogram. And what if I wanted to know what is the total mechanical energy of this bird at this particular instant? Now, as its elevation changes and its speed changes, the number could change. But at this particular moment, what is the total mechanical energy of the bird? Well, we would just use this formula. So it's going to be the kinetic energy plus the potential energy. All right. And so for the kinetic energy, we have 1/2 m, which is 1, times v squared, so times 11 squared. All right. Actually, it should be negative 11 squared, okay, because the bird is moving to the left. But one of the things about kinetic energy is that it involves the velocity squared. So if you are going in the negative direction, you have a if you are going in the negative direction, you still have a positive kinetic energy, because when you square that negative number, it's going to become positive. All right? So the kinetic energy is always greater than or equal to 0. You can never have negative kinetic energy. All right, going back to the example here. Plus the amount of gravitational potential energy, which is going to be 1 times 10 times the elevation, which I'm calling this y equals 0. So 1 times 10 times 12. Okay? So 1 times 10 times 12 is 120. 11 squared is 121. 121 divided by 2 is 60.5. So the total mechanical energy is going to be 180.5 joules. Okay? Boom. So there is oh my gosh, a really important law in physics. It's called the law of conservation of energy. Type it into the chat if you've heard of that before, the law of conservation of energy. So what the law of conservation of energy says is that energy cannot be created What's up, Alex? Nice to hear from you. I hope you're doing well. Law of conservation of energy. Energy cannot be created or destroyed. Okay? It can only be transformed. All right? So energy cannot be created or destroyed. It can only be transformed. So for example, what if, and it can be transferred, I should say. So could I lose energy? Yes. Let's say I lose 5 joules of energy. I can lose 5 joules of energy, but if I lost 5 joules, that means I had to transfer it to something else. So something else gained 5 joules of energy. Okay, so transferring means, you know, I lose 5 joules, you gain 5 joules. Okay. When I say transformed, I mean that it can go from one type to another type. Okay. So I could say I lose gravitational potential energy. And if I lost gravitational potential energy, maybe I gain kinetic energy. All right. So it can be transformed from one type to another type within a particular object, or it can be transferred from one object to the other. So if I wanted to say this mathematically, then I would say that the initial energy is equal to the final energy. So this is the mathematical statement of the conservation of energy. We're going to encounter this word in the class a lot, this word that says conservation. And conservation means that the initial amount, the amount that you start out with, is the same as the amount that you end up with. Okay? So you might have heard of some other conservation laws in your chemistry class. Has anyone ever heard of conservation of mass in your chemistry class? The mass of the reactants of a chemical reaction has to be equal to the mass of the products of the chemical reaction. Okay? That's the law of conservation of mass. There's also a law of conservation of charge. The amount of electric charge that you start out with has to be equal to the amount of electric charge that you end up with. Okay? So those are some ones that you might have heard of in your chemistry class. So, you know, what would be an example of losing? Well, I'll do an example of the reverse. What if you have a roller coaster cart that goes uphill? So this roller coaster cart is coasting and it goes uphill. You can see that its Y value is increasing. Okay? So when this roller coaster starts out, it has all this kinetic energy, and it has no potential energy. So I'm thinking about this as like a bar graph. When it gets right here, it has lost some of that kinetic energy, and it has exchanged it for potential energy. So it gains this much potential energy, so like that. And then as it continues to go up, eventually it'll reach a point where, you know, if you pushed a roller coaster cart up a hill, it's going to go up the hill and eventually it's going to come to a stop, right? So at that point where it comes to a stop, you have no more kinetic energy and you have all potential energy. So these forms of energy are changing from one type to another type. All right? So this would be an example where you are losing kinetic energy and gaining gravitational potential energy. Okay? Let me give you some other examples of transformations of energy. If you burn gasoline, you are taking the chemical potential energy stored in that gasoline and you are releasing it and turning it into thermal energy, into heat. If you have a solar panel, the solar panel is taking the energy from the sun's rays. So that's basically a wave energy because light is a wave. So the light energy comes in, hits the solar panel, and that wave energy is converted into electrical energy. Okay? If you have a dam works by converting the gravitational potential energy of the water into electrical energy. So you have all these transformations of energy happening all around us all the time. Okay, if I move my arm around, I'm taking the chemical potential energy of ATP essentially. You guys know about ATP? And I'm turning it into the kinetic energy of my arm. So that's a transformation of energy. Okay, so let's do an example. And a great example is a roller coaster. Okay, so we have a roller coaster. Okay, and the roller coaster cart starts out right here. There's a person in it who's very happy. They're an arms up person on a roller coaster. Anyone else an arms up person on a roller coaster? Or are y'all arms down? I used to be an arms down person on a roller coaster, but then I was like, I'm going to be an arms up person. And then now I'm always an arms up person. But it took me a while to build up the courage to do that. So here's the roller coaster. It goes wee, woo, 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 like that. Okay? So the roller coaster cart begins at an elevation of 100 meters. And down here, it has an elevation of 35 meters. Okay? And it starts at rest. And once the roller coaster cart gets down here, what I want to know is, what is the velocity of the roller coaster cart? Okay? So I'm going to choose this to be y equals 0, the ground level. And so we use conservation of energy. Initial energy equals final energy. Now, if we look at it, initially we have gravitational potential energy because the roller coaster starts out elevated. So we have mgy. And we would have kinetic energy, but the roller coaster cart is not moving. So we have no kinetic energy to start out with. So once we get to the final point, which is right here, the roller coaster cart is moving. So now we're going to have kinetic energy. Okay? But we still haven't gotten all the way to the bottom, so we still have potential energy as well. We didn't get rid of all of the initial gravitational potential energy. So I would kind of call this the master equation of this problem. Okay? I've identified what forms of energy I start out with. I've identified what forms of energy I end up with. Okay? And it could be just one of them or both of them. Okay? So now I'm going to plug in numbers. Some of you might be alarmed. Why hasn't Mr. P given me the mass of the roller coaster cart? Okay? And you're going to see in just a moment why the mass of the roller coaster cart is actually not important to solving this problem. So let's just proceed. And whenever you feel like something matters, but that number is not given to you, I would always recommend just proceeding as if you knew what it was, but leave it as a variable. Okay? So I'm going to proceed with solving the problem, assuming I know what the mass is, and I'm just calling it m. All right? So I start out with gravitational potential energy. So I have m times gravity, which is 10 meters per second squared, times elevation, which is 100, equals 1/2 times m times v squared. This is what I'm trying to solve for, is the final velocity, okay? Plus m times gravity, which is 10, times 35, which is the final elevation. And one of the things we can see here, and this is why mass doesn't matter, is that every term in this equation has mass. So that means I can divide both sides by mass and cancel it out. So the mass did not matter. It cancels out. So it was not a necessary piece of information to solve this problem. 10 times 100 is 1,000. 1/2 v final squared. 10 times 35 is 350. Subtract the 350 over to the other side. 650 equals 1/2 v final squared. Multiply both sides by 2. 1,300 equals v final squared. Take the square root. V final equals about 36 meters per second. There's a question of how did I cancel out the m's? So anytime you have the same term, so I'm just going to put some numbers in. What if I had like, I'm going to do a little sidebar calculation just to show you how that works. Like what if you had something like 4m equals x times m plus 5m, for example. Then I could collect like terms on the right-hand side, and I would have x plus 5 times m equals 4m. And there I think it's pretty obvious that you cancel it out like that. So then I would get x equals -1. Okay? So it's because every term has mass in it that we could cancel it out. One of the things that I want to show you guys is that we would get the same answer for the final velocity of the roller coaster cart no matter where we decided to put y equals 0. Because remember, I said you get to choose where y equals 0 is going to be. All right? So what if I chose y equals 0 to be right here? Okay? I'm going to redo the problem. And we'll show that we get the same answer. Okay? So once again, I start out with mgy, and I end up with kinetic energy and mgy. Okay? But if we look at it, the roller coaster cart begins at an elevation of y equals 0. So that means that the left-hand side is 0. Then we have 1/2 mv squared. That's what we're trying to figure out. And then we have m times 10 times, what is the final y value? If we choose y equals 0 to be right here, well, because we knew this distance is 100 and that distance is 35, that right there must be 65 meters, right? Because 35 plus 65 would get you up to the top. But we're 65 meters below y equals 0. So our final y value is -65. Okay? So we have 0 equals 1/2 mv squared. minus 650 m. Adding 650 m to the other side, we have 650 m equals 1/2 mv squared. Cancel out the m's once again, multiply by 2, and I can see that the answer is once again square root of 1300. Okay, so we got the same answer no matter where we put y equals 0. That's important. Okay. So definitely the trick in conservation of energy problems is figuring out what is this master equation. Okay. So for example, what if you threw a ball into the air and you want to know, so you throw a ball into the air. You have this ball, you throw it into the air, okay, and I'll suppose it starts at y equals 0, okay, and as the ball goes upward, it's going to lose speed, but it's going to gain elevation, okay. So if we look at it right here, we have kinetic energy. So we have 1/2 mv squared. Here we have elevation, so we have mgy, but we also still have some kinetic energy, just less than what we started with. So I would include a 1/2 mv squared. So this would be the master equation, conservation of energy equation for this problem. Okay? So there's kind of a trick to putting each form of energy on either side of the equation. All right? There's a couple of other thoughts that I want to leave you with before we go to the Zoom room. The first thing I wanted to say is that oftentimes students ask me, like, oh, what if we could find a way to produce energy? We could produce energy out of nothing. And that's a cool idea. That would be awesome if we had infinite energy. Would that break the law of conservation of energy because we're creating energy? And the answer is no. You can never break the law of conservation of energy. If you think you broke the law of conservation of energy, if you say, look it, I'm generating electricity from nothing, electrical energy is coming out, all that means is that you discovered a new form of energy that was unknown beforehand, okay? This has happened time and time again in physics. We think, oh boy, I just broke the law of conservation of energy. Energy is coming out of nowhere. Or, for example, do you know how heat was discovered? How was heat discovered? They were applying the law of conservation of energy, and they found out that the final energy was less than the initial energy. Okay, so they said, oh, the law of conservation of energy isn't true. But then what they decided was, no, the law of conservation of energy still is true, but there's this other form of energy that is being created, and that form of energy is heat. That's actually why it's called internal energy, because it's like energy that's hidden away. It's hard to spot internal energy. So you can the law of conservation of energy is by definition true. If you think that you found a violation of the law of conservation of energy, what you actually did was you discovered a new form of energy that has never been seen before. Okay? So that's my first rant. My second rant is this. Well, this is neither of these are really rants, but another thing I wanted to think about is energy is a lot like wealth. Okay? This is an analogy. Energy is not the same thing as wealth, but it's a lot like, it has some similar properties. So, for example, if you think about wealth, there are different ways that you can have wealth. You could have a house, that's a form of wealth. You could have cash, that's a form of wealth. You could have stocks, that's a form of wealth. You have checkings accounts and savings accounts, and you could have gold bars as a form of wealth. Those different forms of wealth are analogous to the different forms of energy. You have kinetic energy, different types of potential energy. You have heat, internal energy. Okay? And if you think about it, you can transfer wealth. You can hand cash to someone else. That's a transfer of wealth. Similarly, energy can be transferred to another thing. Okay? You can give 5 joules of energy to someone. And just like wealth, if you give someone $5, okay, they gain $5 and you lose $5. Same thing happens with energy. If you give someone 5 joules of energy, they gain 5 joules, you lose 5 joules. Okay? So just like energy can be transferred, wealth can be transferred. Similarly, the different types of energy are like different types of wealth, and that you can transfer between. So what if I have a house and I sell it? I'm turning wealth in the form of property into wealth in the form of cash. Okay? Similarly, the roller coaster is you are turning energy in the form of potential energy into energy in the form of kinetic energy. Okay? I want you to think about it, and we'll discuss this in the Zoom room, but what are some ways in which wealth is not like energy? Okay? Because they're not exactly the same. They have some similar properties. And one last thing that I realized I forgot to talk about, which is, why is energy neat? Why is energy so fun and interesting to work with? Well, the reason is that nowhere in this problem did we reference the shape of the roller coaster track. Okay? This roller coaster track could have been shaped like anything, and we would have gotten the same answer. As long as it starts at 100 meters and it ends at 35 meters, the shape of the track does not matter. Okay? If we wanted to think about this problem in terms of forces, the shape of the track very much would matter, right? Because you have a normal force from the track, and that normal force is always changing directions. Okay? And you have a gravitational force. So this problem would be an absolute mess to figure out in terms of forces. But if we think about it in terms of energy, it's very simple. The track could have been shaped like this. The track could have done this. This could have been the shape of the track. It does not matter what the shape of the track was because the energy is conserved. So that's really, really, really cool. Okay? So that's the thought I leave you with, and I will see you in the Zoom.